Hello and welcome to our lesson on linear functions. Remember, this is a review of linear functions. We've seen these before, but it's sort of through the lens of pre-calculus where we're trying to get ready for the calculus level. Now, it's not that the work we're going to do with linear functions is any different. It's that I want to give you a sort of a background or a little bit of glimpse into what we need this for. Like, what do linear functions have to do with calculus at all? Well, one of the key concepts in calculus, one of the key tools, is the ability to find what we call derivatives. So finding derivatives, again, it's one of the major things that you do in calculus. And very informally, the derivative of a function at any given point is basically the slope of the line that is tangent to the graph of the function at that point. Okay, which sounds like a lot, and I don't want you to get too hung up on this concept because you're going to see it more when you go to calculus. But let's just take this picture for instance. So we have a function here, and hopefully you're recognizing that parabola as a quadratic function. If I wanted to find the derivative, there's a generic derivative for the function that we could find given its equation, but I can also find a derivative at a specific point. So if I wanted to find the derivative of this function at this point here, where we have an input or an x value of 2, what I would need to be able to do is find the slope of the line that is tangent to the graph at that point. So a tangent line is a line that touches a curve at a single point. And that's the blue line that I've put into this picture. So this blue line is a tangent line. It is tangent to that parabola at that point 2, 2. It is the only point where that line touches. And if I can find the slope of the line that is tangent to that parabola at that point, then I can find the derivative of that function at that point. Okay, so essentially, our work with derivatives is going to be completely dependent on our ability to find slope and write linear functions. So they're all interrelated and super necessary. So that's what we're going to take some time reviewing today. What is slope and how do we write linear functions? Because that is going to significantly aid our work in calculus. So slope, we recall, hopefully, is defined by the letter m, but it's a numerical measure of the steepness of a line as well as its orientation. So the steepness and orientation of a line. So when we talk about slope, positive versus negative, that's the orientation. Is it increasing? So the positive slope means the outputs are increasing. Is it decreasing? So we have a negative slope. Our outputs are decreasing in value. So orientation deals with, is it positive or negative slope, which means it's increasing or decreasing. And the steepness would be the rate at which it's increasing or decreasing. So the steeper your line, the faster the rate of change between the points, and the flatter your line, the slower the rate of change between the points. So again, we're going to put a numerical value on the steepness and orientation by doing a one of a few different things depending on the information that we're given. So we're going to define slope by the letter m, and I'm not exactly sure why m is used for slope. I know why s isn't used because s tends to look like a 5. Maybe slope is for the movement between the points. That would be my guess. But we could geometrically just count the rise over the run. So how the rise being the change in the y values and the run being the change in the x values. So if I pick any 2 points on a graph and count the change in y's, or how much it rises from the one point to the next, and the change in x, or how much it runs from one point to the next, I can put a numerical value with the fraction there for its slope. Now if I didn't want to count between the points, I can also find that change in y by subtracting the y values, and I can also find that change in x by subtracting the x values in any 2 points, so I defined those up here, but hopefully this is all stuff that seems familiar. Now I put in the next box here all the different forms of linear functions. Now the first one I want to separate from the other 3. So the first one, the identity function, that is our parent linear function I'm hoping we recognize. We know what y equals x looks like. Our parent linear function, or the identity function, has a slope of 1 and it passes through the origin. So we could say it has a y-intercept at 0. Now that's just the basic linear function, parent linear function that we should be familiar with. All other linear functions are just some transformation of that one. But the next three forms are actually formulas, two that we can use to write linear functions, and one is just a form that we see linear functions in. And so the slope-intercept form, this second box, but it's the first form or formula that we could use. We call, again, slope-intercept form, that's y equals mx plus b. We call it slope-intercept form because in this form we can see, like visually see, the slope and the y-intercept. So the m in this form represents the slope, we just defined that one, and then b represents where the graph is going to cross the y-axis, the y-intercept. And then if we have point slope form, this y minus y1 equal to m times x minus x1, we have m again representing our slope, and then we have x1 and y1 representing some point on a graph, any point on the graph. So x1, y1 represents any point on the graph. And then the standard form, ax plus by equal to c, is not a form that we use, not a formula that we use. The first two we definitely use. So when we're writing linear functions, we will write them in slope-intercept form or point-slope form. If we have standard form, it's because we were given that form, or we're going to take one of the other forms and convert it if that's the form we're asked for, but we don't generally write linear equations in standard form. But when it's given to us, or when we need to convert to it, a, b, and c, the coefficients of x and y, and the constant, those should all be integers. So we don't want any fractions in our standard form. Okay? And all forms are useful in their own ways. I don't know the word, sorry, I lost the word there, but our focus is going to be on writing linear functions, so we're really going to be using the first two, well, the middle two, slope, intercept, and point slope form to do that. So again, linear functions are written in either slope-intercept form or point-slope form. Those are the two forms, the two formulas we will use to write linear functions. And to write either one of those forms, we need two things. Obviously, both forms have m, so m is going to be a necessary component when we are writing a linear function, so we're going to have to know what the slope is, and then we're also going to have to know a point. And in this form, the slope-intercept form, that point happens to be the point where the graph crosses the y-axis. In the point-slope form, the point could be any point on the graph, but we have to know a point. So again, if I know the slope and just some random point, then I'm going to write my linear function in that point-slope form, because that uses any random point. If I know my slope and specifically the point where my function crosses the y-axis, then I can write in my slope-intercept form. And if standard form is required, again, we generally convert to it from one of the other forms. We don't generally write functions that are in standard form. So we could be given standard form or asked to give it. If we're asked to give it, we're going to write one of the other forms and convert. Okay, so we're going to try this out. I'm going to give you some different scenarios, different information, and we're going to practice writing all three of the forms, but you'll see which will be easiest for the different scenarios. So first, we're going to try to write the equation of a line, again, all three forms, and we're given m equals 3 and b equals -5. So obviously, if we have m equals 3 and b equals 5, we can easily plug into our y equals mx plus b form. So in y equals mx plus b form, we input the 3 for m, we input the -5 for b, and we're done. Okay, that would be the most convenient situation on the planet for writing linear functions. Now, if you needed the point-slope form, which sometimes you will, so our point-slope form says y minus y1 is going to equal m times x minus x1. So I'm still going to input the 3 for m, but for the x1 and y1, I need a point. Well, I was given a point. It was just a very specific point. So we have to recognize here, if this is where it's crossing the y-axis, then our x value is 0. So on the y-axis, 0, -5 would be the coordinates, and so the point slope form would be y minus y1 is -5, so minus and -5 would be +5, and that's going to be equal to our slope of 3 times x minus x1 would be 0. And that is, again, what our point slope form would look like. And then if I asked you for standard form, so standard form has the x term followed by the y term and then followed by a constant here, and those x and y coefficients and that constant need to be integers, so no fractions. To get that form, we're not actually plugging anything in. Notice there's no x1, y1, there's no m. So we're just going to take one of the other forms and rearrange it, and I think the first form we have here would be the easiest. So if I took my y equals 3x minus 5 and just subtracted the 3x over, then I would have a negative 3x, a positive y, and then a negative 5 for my standard form. So it's just a rearrangement of one of the other forms, okay? So I think this is, again, best case scenario. If you're given m and b, you should be able to write a linear function in any one of the three forms, and it doesn't require much work. Sometimes a little more work is required, again, depending on the information we're given. So let's look at the next example. This time we're given a graph, and we again want to practice writing the equation of the line in all three forms given this graph. So what information is the graph giving us? Well, pretty much the same information we had in the last problem. So here, for example, I can see my graph crossing the y-axis at -1, and so I know b is going to be -1, or I have a coordinate there at 0, -1. And then I can count my slope from this graph. So if I started at this point, and I'm just going to try to locate the next exact point on the graph, like, oh, my graph is stretched. Why did I do this? That's okay. I'm going to take this, come on, eraser, there we go. I'm going to take this point up here. And remember, you can use any 2 points you want on the graph. I'm just trying to locate a point that has exact coordinates. So like, I thought about considering this point here that has an x value of 2, but the y value would be a half, and I don't necessarily want to deal with the fraction if I don't have to. So I decided to skip that one and go all the way up to this coordinate here. And it's because this is an exact coordinate. It is an x value of 4 and a y value of 2. That makes the counting of the rise and the run much easier. And so if I was to count, how am I moving to get from the first point, the first coordinate 0, -1 to the other coordinate? I have to go, well, two directions. I have to go either right and then up, or up and then right to get left to right. This is how we read a graph, is how we want to move between our points as well. So let's say I go this direction first, and then this direction next. So this would represent our rise, our change in our y values, and that would be from -1 up to +2. So the graph is a little stretched here, but let me change colors. So this is from -1 to +2, that's 3 units. So a rise of 3. And then a run of, this is, again, 1, 2, 3, and then 4. We're going from 0 to 4, so this would represent the run in the graph, and we would say, again, that's going to be 4 units. So I can see on my graph that my slope, my rise over my run, would be 3/4. Okay? So just like the last one, now I have m and I have b. So if I wanted to write my slope-intercept form, I would say y is equal to m, which is 3/4, times x, and then plus b, which is a -1, so -1. And there we have it. Okay, if I wanted my point slope form, then I'm going to use my slope and any point that's on this graph to write that form. So there are actually an infinite number of possibilities for the point slope form because there are an infinite number of points on the graph. I'm going to go ahead and choose to use my y-intercept, or actually, just for variety, I think I'll use this point here at 2, 4, although it doesn't matter. Any point would be fine. So we can take the y minus, I'm going to call this one x1 and y1. So I'm going to say y minus 4 is going to be equal to my m of 3/4 times x minus my x1 of 2. And again, it would not have been wrong to use the other coordinates. It would just be another form of our point slope form. And then for my standard form, I need to take one of these and rearrange it. Again, I think it's going to be easiest to rearrange the slope-intercept form. So if I want to rearrange this one, the first thing I would do is move the x term over. So it's a positive 3/4. I would subtract it. So negative 3/4 x, and then I would still have a positive y there, and it would still be equal to a -1. Now remember, in the standard form, we don't want any fractions, and so we would have to clear them out of this equation. And we can do that by multiplying by our common denominator, or the only denominator in this case, which would be 4. So I'm going to multiply both sides of the equation by 4. So let me multiply this side by 4, multiply this side by 4. So when I multiply here, the times 4 divide 4 cancel, leaving a -3 in front of the x. When I multiply here, 4 times y is going to make 4y. And then on the other side, when I multiply 4 by -4, 4 by -1, I get a -4. And this would be perfectly acceptable for our standard form. Now, some textbooks and some teachers demand that the coefficient of x be positive. I just don't see the necessity for that, and so I'm okay. But if you've seen or heard that rule before, it's debatable, arguable. So if you want to make that positive, you can. If you multiplied the whole function by negative, you could say 3x minus 4y equals positive 4. It would be the exact same function. Okay, just like we have multiple forms for our point slope form, we have a couple of options there as well. The only one that's non-negotiable is going to be the slope-intercept form, because there's only one slope and there's only one y-intercept. All right, so there we have that one. Let's look at number 3, where again we're given a graph. We're going to try to write all 3 forms, but let's see what the graph gives us this time. Notice the graph isn't crossing the y-axis, so we can still use a couple of points to count the slope, but we're not going to be able to plug in b because we don't have it on this graph. So let's first locate a couple of points, any points you want. So I'm going to start here. I can see this one crossing the x-axis at 4, 0. And then I can jump down to any other point I want. I'm just going to use this point here. I can see a point at 5 and then -3. So left to right, to get from the coordinate at 4, 0 to 5, -3, I would have to go down and to the right instead of like I did on the last one where I went up and to the right. So that means the rise in this graph would be a -3 because I went down and to the right to get there. So down would be negative, and then my run is just 1. So I have a run of 1 unit. And then over here, again, to left to right to get from my first point to my second point, I had to go up and to the right, and so we saw a positive slope. Now that's tricky sometimes. We can all count boxes, but sometimes we miss the negative. But remember, if your line is increasing, your slope should be positive. If your line is decreasing, it should be negative. So increasing, positive slope, decreasing, negative slope. So if you don't want to worry about counting, up or down, or factoring the negative in, just make sure you're looking to decide if your line is increasing or decreasing. So in this particular case, I know that my slope is a -3/1, which is just going to be a -3. And then I have a couple of random points. I'm just going to choose to focus on the point at 4, 0. I don't know my y-intercept, but that's okay. So I'm going to let this point represent x1 and y1. Since I have the slope and a point, I'm going to start with point slope form. So in the other ones I had m and b, I started with y = mx + b form. Since I have a slope and a random point, I'm going to start with that point slope form. So I'm going to say y minus y1, which is 0, is going to equal m, which is -3, times x minus x1, which is 4. And so this would be my point slope form. Now how do I get my slope-intercept form? Since I didn't or wasn't able to start with it, is just taking this form and simplifying it. So if I simplified this form, y minus 0 would just be y, and if I distribute the -3, I get a -3x and then a +12, and that's going to be my slope-intercept form. So to get from here to here, just simplify. And sometimes there's a little more work to the simplifying, like if this isn't a 0, then we might have to add that number over, but I think we'll see that in the next, maybe in one of the next two examples. Alright, then the last one we need is our standard form. That's just a rearrangement of one of the other forms. So I'm going to take the one in green here, just add the 3x over. So 3x positive on this side plus the y equal to 12 would be our standard form. And so to go from here to here, just add the 3x over. Okay, so there we have all three forms. Different information given, still really not so bad. Let's look at the next example. So again, try to write the equation in all three forms. This time we're given that our line passes through 2 points. So just like the last one, I had to find the slope first. That's what I want to do here. And I could graph this and count if I want, but remember, when we're finding slope, we're just finding the change in the y values, which I can also find by subtracting my y values, and the change in the x values I can find by subtracting the x values. So I'm going to call this x1, y1, x2, y2, just so I can be consistent here. So I know my slope. Actually, I'm way over here. Let me just focus. Here we go. So my slope is going to be y2 minus y1, so negative 7 minus 3, divided by x2 minus x1, so negative 1 minus 1. And if you were to reverse that, let's say you did negative, or you did 3 minus a negative 7 on the top. So if you wanted to start with this y value, then go here, just do the same thing with the x's, start with this one, and then go here. So it really doesn't matter which points you start with, just start with the same coordinate each time, if that makes sense. So now the top of the fraction, negative 7 minus the 3 makes a negative 10, and then negative 1 minus 1 makes a negative 2, and negative 10 divided by 2, negative 2 makes a positive 5. So now I have my slope, and again I have a couple of different random points, which means I will start by writing my point slope form. And I'm just going to go ahead and use x1 and y1 here. So I'm going to say y minus my y1 of 3 has to equal m, which I just found was 5, times x minus my x1, which was 1. That's my point slope form. So I got one of my three forms. And now I'm going to simplify. So if I simplify this point slope form, then I have y minus 3 equal to, distribute the 5, so 5x minus 5, and then add the 3 over. So y is going to equal 5x minus 2, and now I have my slope-intercept form. And then just a quick rearrangement, subtract the 5x over, so a negative 5x, a positive y equal to negative 2 becomes my standard form. And we did it, okay? Last one, and I saved the best for last, is really the same process we looked at in the previous problem, but sometimes these numbers don't work out so nicely, or we've got fractions we got to be able to deal with, and that's going to be the truth of what happens when you go to calculus. So let's just go ahead and see if we can work with some fractions here. I know that no matter what form I want to write, whether it's point slope or slope intercept, I need my slope first. So I'm going to call this x1, y1, x2, y2, and I'm going to calculate my slope. So y2 is a negative 3 over 2. I'm going to subtract y1, which is a negative 1/2. x2 is 2, and I'm going to subtract x1, which is a negative 1. So it actually didn't work out too badly on the top of the fraction. Negative 1/2 or negative 3/2 and negative 1/2 makes negative 4/2. On the bottom, 2 minus a negative 1 becomes a 2 plus 1, and 2 plus 1 becomes 3. Well, negative 4/2 in the top is negative 4 divided by 2. That's going to be negative 2, and I can't do much with the 3, so negative 2/3 is my slope. Now, I want to use that slope, and I'm going to just choose my first point here to write my point slope form. So point slope form is going to be y minus y1, which is a 1/2, equal to m, which we found was negative 2/3, times x minus x1, which is a negative 1. So minus a negative 1 becomes a plus 1. And then we that's it for the point slope form. Then we simplify to get to our slope intercept form. So if I go to simplify this one, I have y minus 1/2 equal to, if we distribute the negative 2/3, negative 2/3 times x would be a negative 2/3 x, and negative 2/3 times 1 is going to be negative 2/3. And then I have to finish simplifying this, get y by itself, I have to add the 1/2 to both sides, and that's going to give me y equal to negative 2/3 x. And then over here, let's see, if I have negative 2/3 and I have to add a half, I'm going to have to multiply by 2 over 2 here and by 3 over 3 here to get common denominators. So that's negative 4 over 6, and I'm trying to add 3 over 6, which is going to be negative 1 over 6. So negative 1 over 6 is going to be the y-intercept. That's my slope-intercept form. And then lastly, which is good because we're almost out of room, we need the standard form. So that's rearranging. Let's take the slope-intercept and move the x term over. So if I add the 2/3 x over, and then add the y, leave the y, and leave the negative 1/6, that would be the first step. But remember, this can't have any fractions in it. So what I'm going to do next is clear out the fractions by multiplying both sides by my least common denominator. Now the other one I did only had one fraction, but here, 2 fractions, and my common denominator would be 6. So you're going to see why in a second, but I'm going to multiply both sides by 6. As long as I do the same thing on both sides, I'm keeping the balance of my equations, but this will make all of the fractions go away. So when I multiply here, remember this is 6 over 1. So I end up with 12 divided by 3. So in case you're 12 on the top and then 3 on the bottom, so 12 divided by 3 is going to make 4. Oops, pink. So that's going to make a coefficient of 4 for x. And then this one's easy. 6 times y is going to make 6y. So positive 6y equal to, over here, times 6 and divide 6 are going to cancel. Remember the 6 over 1. So I have 6 over 6, which is just going to be 1. And so that's going to be a positive times a negative, so a negative 1. And then we're done. Got the x term, got the y term, got the constant, and I have no fractions left over. So there it is, all 3 forms. Okay? So our ability, again, to write linear functions, regardless of the way we're given the information, is going to be vital to our success in finding derivatives when we get to calculus. So hopefully this was a good review. Hopefully this is all familiar. But as always, if you have questions or need any extra help, then feel free to reach out. Until next time, take care.